In this demonstration, you will learn how ANSYS TurboGrid can be used to produce block-structured hexahedral meshes in the context of an iterative design process. Along the way, I'll demonstrate how to transfer geometry from BladeGen, how to create a mesh, how to transfer the mesh to CFX. TurboGrid is a powerful tool that enables designers and analysts of rotating machinery to create meshes that accurately represent geometrical models. First, I will transfer an impeller's blade geometry from BladeGen to TurboGrid. TurboGrid's viewer allows me to inspect the blade's geometry from multiple perspectives. I can view a single periodic section, or I can view the entire impeller's geometry. As well, the periodic section can be placed in a meridional view. TurboGrid automatically divides the geometry into a set of volumetric regions: the inlet block, the passage, and the outlet block. I can adjust the locations of the automatically generated regions. The parametric option is typically used in an iterative design process because it makes the boundary position designation independent of an axial location. For this demonstration, I will set a shroud tip gap of 3 mm. Note that the topology set object is initially suspended when you start a new case. After making the initial adjustments, I then simply turn off suspension to enable generation of the full three-dimensional mesh. Adjusting the global size factor is a quick way to affect the element size of the mesh. To refine the mesh near the boundary surfaces, I can adjust the boundary layer refinement control using the factor base. You can refine the mesh locally by turning off mesh and geometry visibility, then right-clicking the topology block edge that must be refined. Mesh quality is important because it can influence both the robustness of convergence and solution accuracy. TurboGrid automatically checks mesh quality by calculating a number of metrics. The available mesh metrics include minimum and maximum face angles, as well as element volume ratio. I can visualize any regions where mesh metrics are outside the established quality limits. Even with some mesh metrics outside the limits, I may consider the current mesh satisfactory and use it in my flow simulation. Now that a mesh of the desired resolution and quality has been generated, I can transfer it to CFX and set up a simulation. Any geometric modifications made to the blade will automatically be incorporated into a new mesh. This new mesh can then be simulated in CFX, completing the iteration. This iterative design process can be used to refine specific aspects of the impeller. To demonstrate this, I will modify the blade's leading edge angle in BladeGen. This geometry change can then be automatically transferred to TurboGrid for a mesh update. The mesh topology and all previous settings are retained, ensuring mesh consistency while carrying out iterative refinement. This concludes this demonstration on how impeller geometry changes can be easily propagated to high-quality mesh creation in TurboGrid, delivering a streamlined simulation process for impeller design optimization within ANSYS Workbench.